é pau, é pedra, é o fim do caminho, é um resto de toco, é um pouco sozinho, é caco de vidro, é a vida, é o sol, é a noite, é a morte, é o nascer do anzol, é peroba do cão, é o irmão da madeira, é o matita pereira, é madeira de vento, é um mistério profundo, é o queira ou não queira, é o vento ventando, é o fim da ladeira.
For years now, I have started this lecture with music. And the reason we started this lecture with music is because in the previous lecture, we introduced the concept of a clock, and we talk about the clock period, and we talk about the clock frequency. And sometimes the students will come to me a few weeks after these lectures, and they will tell me, Nelson, I don't really understand this idea of the frequency and the period of the clock. I don't really know how this works in the processor. And then I start thinking that we all know about frequency and we all know about the interval between, for example, the two beats of a drum in a song. We know when it's going fast, we know when it's going slow, we know if it's going slow, the frequency is lower, the amount of time between two hits in the drum is longer. If it's going fast, the frequency is higher and the amount of time between two beats of the drum is shorter. So by bringing music, I try to bring to you one of my principles in teaching, that is to always start with something that you already know. And you already know about frequency because you already know about music, even if you're just an appreciator of music. So we can imagine that inside the processor, there is a drummer that's beating a drum, and the entire processor is functioning to the beat of that drum. That's what we call a synchronous operation. And there are two things that we need to think about this drummer. For one thing, it's really fast. And for another thing, it's really precise. The clock signal is extremely precise, and the amount of time between two transitions of the clock is precisely the same all the time. And the actions inside the processor all happen to the beat of this drum, that's the clock signal. And so now that we have a better understanding for the clock signal, we, in this lecture, will learn a concept that is called the clock per instruction concept, or the CPI, for the execution of a program. And again, keeping the idea that we want to start with something that we already know, I'm going to start with a trip to a store, maybe a trip to the supermarket. And when I went to the store in this trip, I bought three different items. I bought milk, I bought apples, and I bought yogurt. I bought three containers of yogurt, and let's say that the cost of each one was $1.50. 5 apples, each apple costs 50 cents, and two containers of milk, each milk costs $3.50. So now that you know about my trip to the store, you know how many items I got of each type, and you know the cost of each item, you should be able to answer a few questions about my trip to the store. For example, how much did I spend? So if you don't know how much did I spend, you probably could stop the video now and make that calculation yourself. And what you'd be doing is you'll be multiplying the number of items that I bought by the cost per item to obtain the amount of money that I pay for those items. And then you'd add this cost per item to get the grand total of my trip to the store. In this case, I spent $14. And then I could ask you, how many items did I buy? And you'd simply add the number of items of each type, and you'll find out that I bought 10 items. So now that you know that I spent $14 and that I bought 10 items, easily answer the question of what was the average cost per item, and the average cost per item will be the cost, the total cost that you obtain by multiplying the number of items by the individual cost of that item, divided by the number of items that you obtain by simply summing the number of items. So you'd find out that I spent $1.40 per item on average in that one trip to the store. Interesting to note here that if I do a different trip to the store and I get different items or different number of items, the cost per item will be different too, right? That average will change in each one of my trips to the store depending on the items that I get and the number of items of each type that I get. Now let's change the example and let's go back to our example where we have a processor that's rendering an explosion for a movie, for example. So let's say that when rendering that explosion, this processor had to execute 300 branch instructions and 500 arithmetic and logic unit instructions. Arithmetic and logic unit instructions are instructions such as an add, a shift left, a shift right, a subtract. All those are arithmetic and logic unit instructions. And in the rendering of this instruction, this explosion, this processor also had to execute 200 loads and store instructions. And now let's talk about the number of clock cycles per instruction. That is, how long did it take to execute each one of those instructions. So let's say that it took 2 clock cycles to execute each branch, took 1 clock cycle to execute each arithmetic and logic unit instruction, and it took 5 clock cycles to execute each load and store instruction. So now that we have considered that, we can answer some questions about the rendering of that explosion for that movie. We can talk about how many cycles were needed in order to complete the task. And to obtain that, what we'll do is find the number of cycles that were needed for each type of instruction that was executed, given the number of instructions of that type that were executed. And then we can ask how many instructions were executed. So by adding the subtotals for the number of instructions, I get the total number of cycles. And by adding the number of instructions executed of each type, I get the total number of instructions. So now that I have the total number of cycles that were needed to render that explosion, and I got the total number of instructions, I can answer the question of what was the average number of cycles per instruction. And the average number of cycles per instruction will be given by multiplying the number of instructions of each type by the number of cycles that instruction of that type took, and then dividing by the total number of instructions. So in this case, I will find that my cycle per instruction for this specific case of rendering this explosion in this processor was 2.1 cycles per instruction. So this is not the average number of cycles for instruction for that processor. It is the average number of cycles per instruction for rendering that explosion. If I did a different task with this processor, I could be executing a different number of instructions or other types of instructions, and my average would change. Even if I was rendering a different scene in this processor, I may be executing different instructions or different number of instructions of each type, and that will change also my cycle per instruction average. So what we call cycles per instruction is we abbreviate for CPI, that is called clocks per instruction in the literature. So what I have is that I have the amount of time that it takes to do a task and the number of CPU clock cycles that it takes to do that task. So the CPU time, that is the amount of time in the CPU stands for Central Processing Unit, that's our processor. So the amount of time executing in the processor for a given task will be the number of clock cycles that I need to execute that task times the clock cycle time. So that's the clock period, is that interval between two consecutive transitions of the clock signal. So the number of clock cycles also can be expressed as the number of instructions that I have executed times the average number of clock cycles per instruction. Just like if I wanted to know the total amount that I spent when I went to the store, I could multiply the number of items that I got by the average cost per item, and that will give me the total cost. Here, the number of instructions times the average number of clock cycles per instruction, giving it the number of clock cycles that I take to do a task in that computer, for example, to execute a program. Of course, now I can replace one of those expressions in the other. So the number of instructions times CPI can go in place of the number of clock cycles in the expression above. And I can then express the amount of time that I spend in a processor to do a task as the number of instructions that I execute times the average number of clocks per instruction times the clock cycle time, that is also known as the period of the clock. This equation is a central equation for performance analysis in computer architecture. And the reason that this equation is important is because examining this equation, we can see the effect of different changes that I can do to my processor or to my program or to my algorithm, to my compiler, to improve the CPU time. This is to decrease the amount of time that I need to execute a task in the processor. So, for example, if I have another way that I can express the time is using the frequency, and you recall that the frequency is the number of clock cycles divided by the time that it took for that number of clock cycles to occur. For example, if I took 40 billion cycles in 20 seconds, my frequency will be 2 gigahertz. That's the number of clock cycles per second is my frequency. So in this case, I have 2 times 10 to the 9 clock cycles per second. So I can take my expression that I had before that told me that the total amount of time to execute a task in the processor is the number of instructions times the average number of clocks per instruction times the clock cycle time. So this will be the instruction count for the program, and it will be determined by the program, the instruction set architecture, and by the compiler. So the compiler can, for example, eliminate some instructions from the program and reduce the number of instructions. The program, you could change your algorithm, for example, and execute fewer instructions than in an alternative algorithm. And the instruction set architecture, if it has complex instructions, it may need fewer instructions to execute the program. If it only has simple instructions, then it will need more instructions. But there will be a trade-off there. With more complex instructions, you may need more clocks per instruction, so you're going to change the CPI. And depending on the implementation of the architecture, you may end up with a longer clock cycle time too. So those things are very interdependent. The average clock cycles per instruction is determined by the CPU hardware, and if different instructions have different CPI, then the average CPI is also affected by the instruction mix. The instruction mix is what types of instructions did I execute. So in that explosion, maybe I could have done the explosion execute, for example, fewer memory instructions if I did some optimization, and in that case, I could change my CPI. So the compiler can affect the CPI, and also the hardware implementation can affect the CPI. The clock cycle time is usually determined by the technology that's used to implement the processor. Industry keeps trying to increase the clock frequency, which means to reduce the clock cycle time. But the clock cycle time is also determined by the ISA. The ISA is the instruction set architecture. And if I have a very complex instruction set architecture, I may end up with a longer clock cycle because the design is more complex. If I have a simplified instruction set architecture, I may end up with a shorter clock cycle time or with a higher frequency. One of the main motivations for the development of the reduced instruction set computer, that is what RISC stands for. RISC stands for Reduced Instruction Set Computer. One of the main motivations for the development of that technology was to reduce the clock cycle time by reducing the complexity of the design of the processor. So let's work on a small example, a quick example about how we can use the concept of the average number of clock per instruction to do some computation about performance. Let's assume that I have a computer A. My computer A has a clock cycle time of 250 picoseconds. And it has, when it's executing a given program, it has a clock per instruction average of 2. And then I have a computer B. My computer B has a clock cycle time of 500 picoseconds, so it's twice slower. So the clock cycle in computer A is twice as fast as the one in computer B. But my CPI in my computer B is 1.2, so I need much fewer clock cycles per instruction on average to execute this very same program in computer B than I had in the computer A. Let's assume that these two processors have the same instruction set architecture. They are executing exactly the same program. They have used the same compiler, so the compiler did the same code generation. The question is, which one of them is faster and by how much? So I can compute the amount of time that it took to execute the program in the computer A by multiplying the number of instructions that I execute in the computer A times the CPI of computer A times the cycle time of computer A. But I don't know how many instructions I executed. I'm just going to leave a variable k in my equation saying I executed k instructions and I don't know what's the value of k. My computer B, because it is executing the same program with the same ISA and it was compiled the same compiler, is executing the same number of instructions as computer A. So I can do the same and multiply the number of instructions times the CPI of computer B times the clock cycle of computer B. And that will give me the amount of time that I take in computer B. And both of those times are in function of k because I don't know the number of instructions. So I can say that A is faster because A will finish in a smaller amount of time. So A is 500 times k picoseconds and B is 600 times k picoseconds. And now if I divide the CPU time of B by the CPU time of A, I always divide the slower by the faster when I divide in time. I'll find that computer A is 1.2 faster than computer B. Looking into more details, if I have different instruction classes in my program, so for example, some instructions are memory instructions, other instructions are branch instructions, and ALU instructions, and so on, then I can compute the number of clock cycles that I have by computing the average number of clock cycles for each type of instruction times the instruction count of that type. This is very similar with what I did when I went to the grocery store and I multiplied the number of items of each type by the cost of each type. This is exactly what I'm doing. The instruction count of each type is the number of instructions of that type, and the CPI of that type is the cost in terms of clocks to execute the instruction. So CPI is a weighted average. CPI is the number of clock cycles divided by the instruction count. And I can express that as the CPI for each type of instruction times the number of instruction count for the type divided by the total number of instruction count. So this I call the relative frequency of an instruction. So if I tell you that 50% of my instructions were arithmetic and logic unit instructions, I giving you the relative frequency of the arithmetic and logic unit instructions in relation to the total number of instructions that I executed in the program. So now that we understand that CPI is this weighted average, we can do another example. And in this example, I have two compilers that use a different number of instructions of classes A, B, and C for a given program. And the question is, what is the CPI for each versions of this program? So I have the CPI for the class is, for class A, I have 1 clock cycle per instruction, for class B, 2, and for class C, I have 3 clock cycles per instruction. Now I have the instruction count for each one of those types of instruction for each compiler. So the compiler 1 execute 2 instructions of type A, 1 instruction of type B, and 2 instructions of type C. Those numbers are just for this quick example. The number of instructions executed in a real program is very high. And here I have the instruction count for compiler 2. Compiler 2 executes 4 instructions of type A, 1 instruction of type B, and 1 instruction of type C. So compiler A executed a total of 5 instructions, and compiler 1 executed a total of 5 instructions, and compiler 2 executed a total of 6 instructions. So for compiler 1, I have the instruction count is 5. And the number of clock cycles that I needed for compiler 1 will be 10 cycles. And I simply obtain this number by multiplying the number of instructions of a type by the CPI for that class of instruction. So the average CPI for compiler 1 is 2. Compiler 2 executes 6 instructions, but the number of clock cycles for compiler 2 was 9 cycles. And then the CPI for compiler 2 was 1.5. So even compiler 2 execute more instructions than compiler 1, it took less time to do the task when the task was compiled with compiler 2, because compiler 2 used more instructions that had a lower CPI. So if you look in the table, compiler 2 used 4 instructions with a 1 clock cycles per instruction, while compiler 1 only used 2 of those. And on the other hand, compiler 1 used 2 instructions with 3 clock per cycles, while compiler 2 only used 1. So this illustrates that just looking at the number of instructions that a program executes is not a good measure to compare performance between two programs. So summarizing what we have seen performance in this lecture, the CPU time is the number of instructions executed in a program times the number of clock cycles per instruction times the number of seconds per clock cycle. So that is probably one of the most important formulas that we're going to have in computer architecture, and that remains true when you do performance analysis in the fourth year. So the CPU time is the instruction count times the CPI times 1 over the frequency. We could also express that in terms of the clock cycle, that is instead of 1 over frequency. So the performance will depend on the algorithm, which affects the instruction count and possibly the average number of clocks per instruction. On the programming language, that will affect also the instruction count and the CPI. On the compiler can affect the number of instructions that's executed by the program, but also the CPI, as we saw in the previous example, by choosing instructions that have a lower CPI. Even if it has to execute more of those, it can end up with a performance advantage in the end. And the instruction set architecture will affect the number of instructions executed, the CPI, and the frequency. So, and recall, if you find yourself lost about the concept of frequency and clock cycle, think about music. You already know all that you need about frequency and clock cycles. And then when think about CPI, think that this is simply a weighted average, the same kind of average that you know how to compute when you do something like a simple trip to the grocery store where you buy different number of items that have different costs. So one of the main motivations for this lecture was to show you that you already know these concepts. All that you need are some new terminology that is the terminology of computer architecture.